Okay, welcome everyone to Zach's seminar. It's my great pleasure to introduce Jun Hoch from Institute for Advanced Study, Princeton, and Jun will tell us about Lorentzian polynomials.
Okay, well, I've changed my affiliation, so it's Princeton University at Princeton. But well, anyway, thanks for coming here and thank you for the invitation. I'm very happy to meet you guys in this new normal setting. So I'll tell you about this class of polynomials, multivariate polynomials that I and my collaborator Patrick Brandon calls Lorentzian polynomials. And I mean, logically speaking, this whole theory is some glorified multivariable calculus. So nothing to do with algebraic geometry, for example. And I have given this talk a few times in various settings to general audience, like hiding most of the algebraic geometric motivation for the main definitions and theorems. But really, at least for me, the whole project had a very concrete root in a certain basic considerations in algebraic geometry. And there are some questions left that I find fascinating. So I thought it would be worthwhile to share this story with algebraic geometers. But please do keep in mind that every statement and every proof that I may or may not speak about are really just calculus. But the role of algebraic geometry in this project is it tells you what to prove and oftentimes how to prove them. And without those guidance, I suspect some of the statements are rather tricky to prove. So the topic is Lorentzian polynomials, and very on a bird's eye view, the reason I find it fascinating is because this class of polynomials naturally link two different notions of convexity. So one is our usual familiar notion of convexity of functions, say continuous functions or more general functions. And the other convexity that I will briefly introduce later in the talk is the notion of discrete convexity, rather well developed subject in the optimization theory circle, but not as well known to the other classical notion of convexity. And these two notions of convexity is related to two different ways that you can view a polynomial as a function. So let me introduce some notations that I'm going to use throughout this talk. So the main player will always be a homogeneous polynomial f. And I will going to write down f in a specific way. So it's a polynomial, it's a sum of many terms, and the terms will be labeled by alpha. And the main thing that I wish to emphasize is that I'm going to always write my polynomial in this normalized way. So as if you would write a Taylor expansion of some polynomial. So when I refer to coefficients, C alpha of f, I'm referring to these numbers that you see in front of the monomial W alpha divided by alpha factorial. So here, C alpha will be always a real number, and in my setup, a non-negative real number. And alpha will be a vector of exponents decorating the monomials. So it's alpha is an element of the non-negative part of C to the n. And as usual, W alpha over alpha factorial, by that, I mean really this exponential monomial divided by alpha I factorials. And as you'd expect, the reason why I'm writing my polynomials in this normalized way is because the differentiation plays an important role in the theory. And if you normalize this way, the normalized form doesn't change when you differentiate. So the differential operators are going to use this notation, partial to the alpha, which I mean you differentiate alpha 1 times with respect to the first variable, alpha 2 times for the second variable, and so on. Okay. Going back to the main story, the two different ways that you can view a polynomial as a function is this. And for our context, it's better to focus on the non-negative parts. So the first is the usual way. So I'm going to view a polynomial as a function from Rn to R. And this function sends W to Fw. So its value at F, the value of F at W. And on the discrete side, the function that I'm talking about goes from Z to the N to R. And it is the function that sends alpha to C alpha. So on the second case, I'm really viewing just the polynomial as a collection of its coefficients. But it's not just an abstract set of coefficients. There is a geometry here because the domain has a geometry. Because you should more think of it like an array of coefficients arranged a certain way. And that geometry will play an interesting role in the theory. So the main result that I'm going to introduce later, if you state it very roughly, says that the convexity of this continuous function f is related to the convexity of this other discrete function f in an interesting way. I'll gradually make this statement more and more precise. But before telling you either definition or the main theorem of this theory, let me first show you one of the many applications of the theory, because this application sort of highlights the challenge to algebraic geometers, or at least it should puzzle you a little bit what this theory is really doing. So I'm going to introduce a specific conjecture in combinatorics, specifically in matroid theory. The conjecture is most elementary and easy to state in terms of linear algebra, so let me stick to that setting without telling you what a matroid is. So let's say you have a set of n vectors, and let's call the set of vectors A. Just you have some finite dimensional vector space over some field, and you pick n different vectors in any way. And this choice of A gives you a sequence Fk, which counts the number of k element independent subsets of A. So here, independent, of course, refers to the linear independence of vectors. So I have some vector arrangement, and I count the number of independent sets according to their cardinality. So let's do an example. So this is our favorite example of all 7 non-zero vectors in 3-dimensional vector space over F2. And we like drawing this arrangement in this picture using the picture of P2 over F2. For this configuration of vectors, the sequence that I'm talking about starts with, just like any other configuration, 1. which counts the number of zero-element independent subsets of A, and there is one, which is the empty subset. And there are 7 one-element independent subsets corresponding to 7 non-zero vectors. And F2, that should be 21, because 21 is really 7 choose 2. And if you pick any 2 vectors, they will be independent. F3 is slightly more interesting, because if you compute 7 choose 3, you get 35, but not all triple of vectors are linearly independent. There are exactly 7 dependent triples corresponding to 7 lines in the P2. So you get F3 equal 28. 1, 7, 21, 28. This is the sequence that I'm talking about in this specific example, but you can imagine some crazy arrangement of vectors and you get certain sequence of numbers. And the conjecture, due to John Mason from the early 70s, is that no matter which A you start with, you always get the following so-called log concavity inequality. So you divide Fk by n choose k. Remembering that n is the number of vectors. And then you should always get a log concave sequence for any index like k. And I guess, the intuition or just a way to think about this conjecture would be the following. So if you start with an infinite field in some dimensional, finite dimensional vector space, and if you have picked your vectors randomly, then your Fk will be, of course, n choose k, because there are no unexpected dependencies. And in that case, you see that the inequalities are tight. Every entry is really 1. And the content of the conjecture is that as you specialize your vector configuration, maybe by moving the vectors or changing the field into a smaller one, the inequality always fails in the one way, showing you this sort of a cavity. And if you know what a matroid is, or if you wait until I tell you what a matroid is until later in the talk, you will see that the same conjecture makes sense and is expected to be true for arbitrary matroid, which you can think as sort of an abstract point vector configuration. And one thing that you can do with the theory of Lorentzian polynomial is that you can prove this conjecture more generally for any matroid. And by the end of the talk, you will hopefully agree that the proof that I'm going to show you soon is clearly motivated by algebraic geometry considerations. But logically speaking, we still, at least I and people I know, do not yet know algebraic geometry proof. Even when your vector configuration lives over some familiar and easy fields like the field of complex numbers. Okay, do we have any questions at this point? Okay, so far pretty easy. I mean, this is a statement in linear algebra, so you expect that there to be an easy proof, and somehow it had eluded us for 40 years. And I think the reason why people have found hard proving statement like this is that the theory of Lorentzian polynomials, which I find it very effective and very beautiful, is somewhat unnatural if you don't think it in terms of algebraic geometry. But if you are an algebraic geometer, you should think that this is just a piece of cake. So let me show you the motivation. And I hope this all makes sense and I feel very comfortable to all of you. And the motivation goes like this. So think of your favorite D-dimensional projective variety and pick some Neff divisor on your projective variety. But maybe you pick N divisors. And by the way, I'll be going to be very consistent on my use of the variable N. So N was the number of variables in my polynomial. And in the context of Mason's conjecture, it was the number of vectors. And in this motivation, it's the number of Neff divisors that I'm talking about. And D will be the dimension of the projective variety or degree of the homogeneous polynomial F that I talked about earlier, or the dimension of the vector space where the vector configuration lives in the context of Mason's conjecture. So whenever you have this collection of Neff divisors, you consider this polynomial labeled by H, the collection of Neff divisors. So the wi's are my variables for the polynomial. You take the linear combination of hi with respect to wi, and you take the d power and take the degree. And you divide by d factorial, which is mostly for cosmetic purposes. Things tend to look better when you divide by d factorial. Not really relevant to the logical core, but let's just put it there. And there are obvious things that you immediately notice about FH, namely that it is a degree D homogeneous polynomial in n variables, W1 to Wn, and it has non-negative coefficients because I'm assuming that all my HI are Neff. And the motivating question is, in general, for any Y and any H, what else do you know about this class of polynomials that can arise as FH? And other than this non-negative coefficient thing, I only know one other fact about this FH. And that is the fact which motivated us to define the class of Lorentzian polynomials. Or you can say that it's the notion of Lorentzian polynomials is engineered in such a way that FH is a Lorentzian polynomial becomes a question to the question, what else do we know about this polynomial? But of course, the question itself is sensitive to who do we actually mean by we in the sentence, what else do we know? And by we here, I meant I and my collaborator, Petter. But maybe you will notice something else. And maybe that is why I am giving this talk to you right now. So see if you agree that the question to this, the answer to this question is FH being Lorentzian polynomial. So I'm going to structure this talk in a somewhat unusual way because I think this is more informative to give you the question before losing your attention when the talk goes on for another 20 minutes. So before telling you what a Lorentzian polynomial is, and before telling you what properties this class have, I'm going to show you how to prove this Mason's conjecture, this linear algebra statement, using the theory of Lorentzian polynomials. And it's basically one page if you accept certain things. So here it goes. Somebody gives you a vector configuration. You want to justify this log concavity inequality. How do you do that? You first consider this homogeneous generating function for the independent subsets of A. So there are going to be these n variables corresponding to the n vectors in A. And there is one more variable, W0, which I'm going to use to homogenize my generating function. And what generating function am I talking about? It's the generating function for the independent sets. So you're going to sum over all independent subsets I of A, and there will going to be a corresponding square-free monomial, Wi. I hope the notation makes it clear which monomial I'm referring to. So it's the one corresponding to an independent subset. And I just use my extra variable W0 to homogenize the whole thing into degree n. And the main point of the proof, probably the most important line in this whole proof, is this. It is straightforward to check that this FA is Lorentzian. Of course, I have not told you what Lorentzian polynomial is, but for the moment, you can think it like it has the analytic properties of the volume polynomial of certain Nav divisors on a certain projective variety. You don't know actually this projective variety actually exists, but let's just pretend that it's a volume polynomial. If you accept that statement, then it is easy to believe the following reasoning. Therefore, the following specialization is Lorentzian as well, where I keep my W0 and set all the other variables equal to each other. So in the geometric setting, this is like setting all these corresponding Nav divisors equal to each other. And then what do you get? So all these monomials collapse into a single power of a variable, and your polynomial becomes essentially a one variable polynomial or a two variable homogeneous polynomial. And the degree k part in W1 counts, of course, the number of k element independent subsets of A. And you want to write this polynomial in a normalized form using this exponential monomials. And the normalized coefficient you get is exactly the quantity of interest, Fk divided by n choose k. So this 1 over m factorial is subsumed into this expression. But the theory of Lorentzian polynomials in two variables is extremely simple, as you will see. And it more or less just says that this sequence of normalized coefficients, Fk over n choose k, is log concave. And that is the end of the proof. So you will see that like modulo definition, I have used very few properties of Lorentzian polynomials. So I have used the property that I know what the Lorentzian polynomials are in two variables. And the class of Lorentzian polynomial is preserved under specialization by setting variables equal to each other. This is not a big deal. But the real magic in this whole proof is hidden in this line, as I have emphasized before. It is very easy, either for computers or for us humans in specific contexts, to check that whether a given polynomial is Lorentzian or not. This is a miracle, as I'll try to suggest. All good so far? Okay, so now I'm going to define the class of Lorentzian polynomials. So from now on, well, for the next 20 minutes, it's this multivariable calculus part that I'm referring to. So we are actually going to do some mathematics, but it's not a terribly deep one, but I hope you will find interesting. So I'll step by step define this class of Lorentzian polynomials by sort of a very elementary induction on degree. So every action will happen on this space HDN. This is a set of homogeneous polynomials of degree d in n variables with real coefficients. So I'm talking about finite dimensional real vector space, and all the actions will happen in this vector space. So our coefficients. And I'm going to start by considering the case d equals 2. So this is like a base case. And in this case, I'm going to define a subset of H2n, in fact, an open subset. Which I write by L naught of a 2n. So this little circle there is to indicate that this is an open subset. And it's a set of all quadratic forms with positive coefficients that have the Lorentzian signature, by which I mean exactly one positive eigenvalue and all the rest being negative. So this is an open subset. So all positive coefficient, that's an open condition, and have this Lorentzian signature, which is also an open condition. So I have an open subset. And for general D, I'm going to define an open subset of HDN, denoted by L naught of a Dn. And this is by definition what I'm going to refer to as a set of strictly Lorentzian polynomials. And it consists of homogeneous D forms in n variables with a property that its ith partial derivative is in L naught of D minus 1 n for all I. So simple. I mean, so if I give you a homogeneous polynomial, it's a completely trivial task to check whether it is strictly Lorentzian or not. You just take partial derivatives in all possible ways until you get quadratic forms. So you get a bunch of maybe a few hundred quadratic forms, and you see whether they all have the Lorentzian signature. And of course, all the coefficients of the original polynomial must have been positive, by which I mean strictly positive. And this is the definition. And by Lorentzian polynomial, I mean the polynomials in the closure of L naught Dn. So this is the closed subset of HDN. So now I have given you a definition, and maybe you see where I'm coming from in the context of my previous algebraic geometry question. So what do we know about these volume polynomials of Neff divisors on projective varieties? Well, I know that they must be volume polynomials of limits of volume polynomials with respect to ample divisors. But when all the divisors are ample, I know when d equals 2, so I'm considering the case of a surface. I know we have a Hodge index theorem for surface, so I know it should have this signature. And in general, since my all divisors are ample, I can cut it by those divisors staying in the family of irreducible projective varieties. And I cut it until I get to the case of surfaces. I should have that signature. And of course, all the coefficients now should be positive if you play with ample divisors. So that is the definition, but forgetting the geometric picture for the moment, let's ask ourselves this question. This is a question in calculus, right? So you're given this definition. If somebody asks you this, I give you a polynomial and your job is to check whether the given polynomial is Lorentzian or not. And just looking at the definition, this question appears as if it is a very hard problem. I mean, by hard, even if you are allowed to, I mean, maybe you're given like a 5-variable polynomial in degree 4, and you are allowed to use maybe Wolfram Alpha or maybe supercomputers at your disposal, and then somehow you type some command, and how do you check whether the polynomial is Lorentzian or not? If you want to show that the given one is Lorentzian, you have to somehow produce an explicit limiting sequence of strictly Lorentzian polynomials. And if you want to show that the given one is not Lorentzian, you have to somehow argue your way to show that the given polynomial does not have the property that general Lorentzian polynomial has. So here is maybe the simplest possible example. A case when D is 3 and N is 2. So cubic forms in 2 variables, and maybe somebody gives you the sum of 2 cubes, W1 to the cube and W2 to the cube. And you are asked whether this is Lorentzian or not. Well, we don't have an obvious algorithm for testing, but since, as you see in the definition of strictly Lorentzian polynomials, the taking the derivatives is built into the definition. So it looks like a good idea to first take the 2 derivatives and see whether they are Lorentzian. So if you take the first partial derivative, you get 3 over W1 square, and similarly for the second one. And it is easy to see that both are in fact Lorentzian. So I can add to this polynomial 2 epsilon W1 W2 and maybe epsilon cube W2 to the square. And that corresponds to the quadratic form you write in matrix by 3 epsilon 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 cube. Now this new 2x2 matrices with epsilon positive but small have all entries positive, and their determinant is negative. That's why I have used the cube here. So therefore, it must have 1 positive eigenvalue and 1 negative eigenvalue. So this is Lorentzian. And same for the second partial too. But the subtlety of the whole thing is that each partial being Lorentzian does not imply the original polynomial being Lorentzian. So what's happening here is that you have this open subset L naught of a 3, 2 living inside this 4-dimensional real vector space. And our sum of 2 cubes is somewhere far away from that open subset. Well, that is a claim. And later you are going to see general statement which makes sense of this. So maybe a small challenge for you now is that now you have seen the definition of Lorentzian polynomials, whether you can see the sum of 2 cubes not being Lorentzian. So what happens is that you can approximate each one of the partials using strictly Lorentzian polynomials, but you can never make the 2 approximations compatible in the sense that it's coming from an approximation of F itself. Questions? Okay. So in order to introduce the key definition to be used in the main theorem, let me digress into the realm of discrete convex analysis. So this whole thing extends the theory of matroids, and the main definition, which is very simple to tell, but earned after the generations of hard work by excellent mathematicians like Whitney Lovas, Edmund Gelfand, Gureski, Macpherson, and so on. And the main definition is that of generalized permutohedron. So it's a polytope in Rn, all of whose edges are in direction EI minus EJ. And here EI is the standard height basis vector of Rn. So these are the polytopes living in Rn, all of whose edges point to a root in root system of type A. And this picture you see here is the picture of the permutohedron in R4. I have one in my office. You can order one in Amazon if you know how to Google or search correctly. Not too expensive. And you can stack them if you have many. You can tile the whole space using this one. And the connection to the theory of matroids was noticed after the work of Gelfand and Goreski-McPherson, who computed the moment polytopes of torus orbit closures in Grassmannians. So if you take a point in the Grassmannian, look at the torus orbit, take the closure, that's a toric variety. And what's the polytop? That's the polytop that's known as the so-called basis polytop in matroid theory. And they noticed that, in fact, the whole axiomatization of the matroid theory can be just simply stated by saying that all the edge directions of this basis polytop are in direction EI minus EJ. So this gives you, well, okay, so let's not digress too much. I have told you a class of polytopes. And the slogan of discrete convex analysis is to take this as a definition. So a discrete convex set is a set of all lattice points of an integral generalized permutohedron. You can take that as a definition of discrete convex set. More technical name for a discrete convex set is an M-convex set. So let's call a subset J of C to the N, maybe in the non-negative part, if it satisfies, well, if it is the set of lattice points, all of them, of an integral generalized permutohedron in Rn. So there is a bijection between integral generalized permutohedrons and the collection of M convex sets. So just think of generalized permutohedron and all its lattice points. And if you already know what a matroid theory is, this statement with lots of quantifiers is there to show you that this definition 1 is equivalent to the definition that you see in matroid theory, the basis exchange axiom. So we would not need to go into this. But let me just point out that you can define a matroid or its set of bases to be the M-convex set, all of whose points are 0, 1 vectors. Or you can also say that equivalently that a matroid is a generalized permutohedron, all of whose vertices have 0, 1 coordinates. And if this happens, any lattice point in it must be a vertex. Okay. Any questions? So let me show you some M-convex sets in case you have not seen much of them. So the most famous ones comes from graphs. So you take any connected graph with n edges, and the M-convex set associated to this graph is the set of all spanning trees of G. And I'm going to view the set inside Z to the N. By which I mean I'm going to view each one of the spanning trees as a subset of edges of G. And each edge in G will be a coordinate in Z to the N. So a spanning tree is a subset of edges. So every one of the spanning tree, I'm going to think of it as a 0, 1 vector. So 1 if the edge is in the spanning tree, 0 if not. So for example, if you have K4, according to Cayley's formula, you should see 16 spanning trees. 4 to the square, and here they are. And all of them has 3 edges. So I'm thinking of vectors like 1, 1, 1, 0, 0, 0, and so on. Depending on how you order the edges, not so relevant. And the claim, which is non-trivial if you don't know macro theory, is that this collection of 16 lattice points is an M-convex set. So its convex hull is a generalized parameterhedron, and the 16 vectors are the set of all lattice points in its convex hull. Another classical family of examples, which is more relevant to this Mason's conjecture, is that the ones coming from vector configurations. So as before, let's say A is the set of n vectors in a vector space. And for this J, you take the set of all bases of the ambient vector space that's contained in A. Again, I'm going to view this as a subset of Z to the n. Here, n refers to the number of vectors. So for example, if you have 4 general vectors in R2, so maybe I have 1, 2, 3, 4, then I have 6 bases for choose 2. In fact, you have 1, 1, 0, 0, and so on. If you take the convex hull, 4, you see an octahedron, and you can see that this octahedron is a generalized parameterhedron, and it has 6 lattice points. But you can do this with any vector configuration, and you always end up with a generalized parameterhedron. That's the claim. Good. Questions? And the reason why I have told you what an M-convex set is to tell you this definition of MDN. So it will going to be a set of homogeneous forms of degree D in M variables with a property that its support, viewed as a subset of Z to the n, is M-convex. And by support, I simply mean the set of all monomials that appear in F. So if you take the convex hull of support of F, you get the so-called Newton polytope of F. And I'm referring to the lattice points inside the Newton polytope. And I want this to be M-convex. So this MDN is a funny set. It's neither open nor closed in HDN, dictated by some funny combinatorial criteria. And again, I'm going to introduce some symbols, L2n. And I want this L2n to be the closure of L not 2n. So by definition, I take it to the set of all quadratic forms with non-negative coefficients and that have at most 1 positive eigenvalue. And still, we are defining some symbols. And I'm going to take as a definition LDN to be the set of all F with a property that is ith partial belongs to L of a D minus 1n for all I. And the key thing here is, in addition, I require my F to have a support that is convex in the sense of discrete convex analysis. So basically, I want the class of polynomials with right signature properties, and in addition, Newton polytope being the generalized parameterhedron, and I don't want to miss any monomials in the interior of this, inside this generalized parameterhedron. So for example, if you go back to our example of this sum of 2 cubes, its support consists of 2 points, and it misses the interior 2 points corresponding to W1 square, W2, for example. And this is not an M-convex set. I mean, the convex hull is generalized parameterhedron, all right, but I'm missing 2 points. And the main theorem from which most of the other things follow is that this LDN is the set of Lorentzian polynomials. So there are really 2 inclusions here, this and that. And both are, I think, non-trivial. So one claim is that if you take strictly Lorentzian polynomials and take limit to set some of the coefficients equal to 0, then the limiting set must have M convex support. So generalized permutation must appear. And conversely, if you have a polynomial with the right signature properties and in addition support coming from generalized permutation, it must be approximable by strictly Lorentzian polynomials. So this in particular tells you that LDN is a closed subset of HDN. And if you think about it, it's kind of crazy because it's not being in MDN is not really a closed condition. But when it interacts with the signature condition, it somehow miraculously becomes a closed condition. And furthermore, if you look at the same set inside the real projective space, and the whole thing is preserved by scaling by a constant. So you just look at the things inside the projective space, then you get a compact and contractible subset of the projective space, and it has a contractible interior. So this compactness is one consequence of this LDN being closed. And although LDN is not convex, it has this ball-like quality. And in fact, this PLDN is really a closed ball. So this fact was conjectured in my paper with Petter, and recently Petter announced the proof of this statement, which is rather delicate. So we want to show that something is homomorphic to a ball, and sometimes that's not so easy to do. But in this case, it can be done. And you can say much finer things about this space of Lorentzian polynomials. So let's say Lj is the set of Lorentzian polynomials with given support j, for whatever j is. And the fact is that this Lj is non-empty if and only if j is M-convex. And in this case, its image in projective space, deformation retracts to a distinguished point, which must be, of course, the generating function for j. So you sum over all points in j and put all the coefficients equal to 1. And that is Lorentzian, exactly when j is M-convex. And there are some interesting statements, like any non-negative linear change of coordinates preserve LDN. If you still have this projective geometry picture, that's maybe kind of obvious. But if you think of this definition of LDN that involves generalized permutation, that's a little bit surprising, because if you change coordinates, then the support changes in somewhat unpredictable way. And I'm saying that one generalized permutation always turns to some other generalized permutation. And here, linear change of coordinates, I mean not necessarily invertible. So for example, you can set all the some of the variables equal to each other, as we have done in the proof of Mason's conjecture. And let me skip 4 and 5. The point being, then you can characterize this class of polynomials by some analytic condition. And there's this study of recently popularized the stable polynomials in the context of Cadiz and Singer conjecture and so on. These are all Lorentzian, and this is where my collaborator Petter is coming from. And for any convex sets, delta 1 to delta n in RD, the volume polynomial corresponding to this choice of convex sets always belongs to LDN. And from my point of view, this is at the heart of the so-called Brun-Minkowski theory, computing volumes, mixed volumes, and stuff like this. And more generally, as I have told you before, and as you will immediately recognize, for any projective variety y and f divisors d1 to dn, the degree polynomial belongs to LDN as well. And you can develop the whole theory, not just over this particular real closed field that we call R, but any other real closed field like the Pujo series field, RT, and then you can essentially get the same theory because at the level of pseudo logic, everything's the same. But in addition, now you can tropicalize things, and then you can relate Lorentzian polynomials over RT with discrete convex functions instead of discrete convex sets, and so on. But let me just, before ending the talk, let me show you or highlight one of the basic consequences of this consideration, which is that you can develop a theory of Lorentzian preservers. So producing a large family of linear operators that preserves the class LDN. And one consequence of this theory is that the linear map that sends a polynomial f to its square-free part. So just throw away all the monomials that contain square or higher order terms. And this funny linear map preserves LDN. And one consequence of this observation paired with observation number 7 is that if you start with any projective variety and you pick any set of Neff divisors, and then you have a volume polynomial, and the set of monomials that you see there corresponds to those indices where the corresponding Neff divisors has non-zero intersection. But if you just look at the square-free part, and then this is what you would call maybe a dual complex of the given set of Neff divisors. Just collect all the D collection of Neff divisors that have non-zero intersection number. And then you notice by this whole thing that you must always get a matroid, the set of bases of a matroid, because it supports the square-free part is Lorentzian, its support is M-convex, but now you have monomials that have 0, 1 exponents, and that's exactly matroids. So this is how you would arrive at the theory of matroids if you were algebraic geometer or projective geometer and never heard of matroid theory before. So this is a situation. So for every given D and every given N, you have this ball, the Lorentzian ball. And its interior is an open ball. If you take the closure, you get a closed ball. But this is a very interesting ball, like a soccer ball, which has a smooth thing, but very interesting discrete structure on the boundary. On the boundary, you see some pieces that you may call stratas. And each piece is also contractible and contractible to a distinguished point. In fact, every piece, we know that exactly every piece is labeled by every one of the M convex sets. So generalized permutohedrons. So the point is that you see all the generalized permutohedrons, in particular, all the matroids, not excluding any single one of them. And every one of them give a contractible piece on the boundary. And the way these pieces are organized shows you interesting information on degeneration of Lorentzian polynomials, like this non-final configuration degenerating to a configuration with one less basis, and so on. But since it includes all the matroids, in particular, it includes all the graphs that as you increase D and N, but it also includes all the so-called non-realizable configuration, like the one you see here. This is the non-Pappus configuration. And if you like the theory of finite projective planes, you will know that the non-existence of this 9-point configuration, where the 3 points in the middle are linearly independent, is the necessary and sufficient condition for your projective plane to be coordinatizable over field. So this is like a prototypical example of a non-realizable configuration, but still, this is a generalized permutohedron. So if you look at all the triples that are not on a line in this picture, that's an M convex set. And there is a corresponding piece in our Lorentzian ball. And in fact, this matroid is not so non-realizable if you are a projective geometer. So in fact, there is a certain projective threefold and 9 Neff divisors corresponding to these 9 points that you see here. So that if you take the dual complex, then you get exactly the generalized permutohedron given by this picture of the non-Pappus configuration. And that one is on the boundary of the Lorentzian ball. So just to paraphrase the question that I have posed earlier, in blunt terms would be this. In constructing the theory of Lorentzian polynomials, I have really used one input, namely that I know the Hodge index theorem. And then I forgot of geometry and then just built an analytic theory that incorporates the theory of Hodge, this Hodge index theorem into account. And the question that you may obviously ask is that did I miss anything? Is my definition correct? On the one hand, since the final answer is so beautiful, that like the closed ball and the boundary strata exactly labeled by generalized permutohedrons, you are like inclined to believe that you started with the right definition. But on the other hand, if somebody asks you this question, is there any Lorentzian polynomial that is provably not a limit of, say, volume polynomials of Neff divisors on a projective variety, maybe over some field? Then it is very hard to give positive or negative answers. So for example, if we go all the way back to the proof of Mason's conjecture, and now you would believe everything I have said here. It's straightforward to check that this particular polynomial is Lorentzian. I just checked that its support is M convex. That's basically matroid theory. And you check this signature condition that comes from induction, basically. But if you ask, say you start with a vector configuration with on a complex vector space, and if somebody asks you, can you find a complex projective variety with n Neff divisors on it, whose volume polynomial is exactly this generating function? Then question like this is very tricky and not so easy to answer. And particularly in this example, I don't know how to answer. But in general, I don't know a single polynomial that is single Lorentzian polynomial that is provably not a volume polynomial of Neff divisors. And you can, of course, make the question harder by putting these expressions like this. But even without those, I mean, we lack fundamentally, I think, to have an ability to answer questions of this form. I don't know whether you should expect yes or no, probably no, but just the tools, I will just want to point out that it seems like the tools are not readily available. Okay, that's it.
Thank you, June. Okay, let's thank June in Zoom. Okay, thank you. Thanks for great talk. Questions? If you have any questions, you can type in chat or you can just speak. I have a general question. Just do you have more problems about algebraic varieties, which basically inspired from Lorentzian polynomials, or only this one which you asked?
I mean, you can get like many sub-problems by specifying a specific polynomial that's given by combinatorics or whatever, and ask whether that specific polynomial is a volume polynomial of projective variety. Or you can ask a rather general problem to write down any single polynomial, Lorentzian polynomial, that is provably not a volume polynomial. And these two have a very different flavor. I mean, one, probably these have like a beautiful positive answers that's not so easy to find, and it will involve, like it will motivate us to find some beautiful and clever construction of projective varieties that model the given combinatorial situation. And for the general problem, and if you want to say that the answer is no, which I think is the expected answer, it is also very interesting. It forces you to write down an explicit and concrete Lorentzian polynomial, and you have to somehow argue that this does not come from algebraic geometry. But then it's not about the clever choice of the polynomial. Then you have to find a general theory that applies to projective varieties, no matter how singular or whatever, in no matter what field, and it should apply, you should find the property of the volume polynomial that holds for all such things that does not apply to your cleverly chosen polynomial. And this is also, I think, very like a challenging and interesting thing to do.
Thank you, June. June, there's a question in the chat. Do you want me to read it or you read it?
Was the start of the project trying to attack Mason's conjecture, was finding the notion of Lorentzian polynomials and then finding an interesting application? It's hard to say. So these two things were always on the back of my head. So one thing is like this, of course, this very concrete Mason's conjecture. And the other thing was this, this Minkowski's volume polynomials that I have briefly mentioned. So it's basically the same thing where you have convex sets instead of Neff divisors. And if you know like a toric geometry, this is like a sub-problem. So any convex set can be approximated by rational convex polytopes. And then this Minkowski polynomial becomes a special case of Lorentzian polynomials. And for the last 100 years or so, it has been vaguely asked in various forms whether the known Brun-Minkowski inequalities are a complete set of inequalities that you can expect for mixed volumes of convex bodies. And this is like saying, this is like a convex body version of the question that we have talked about. And that one was on the back of my mind. And if you said it this way, and you can see immediately that the answer is no. So for example, if you look at this particular point on the boundary corresponding to the Fano configuration, you see that it is not the volume polynomial of 7 convex bodies, because this is like a square-free polynomial. So all the volumes are 0, and many other mixed volumes are 0. So 7 convex body must be like line segments. This is a small lemma there. But then those line segments should live in vector space over R, contradicting the fact that this Fano plane only lives over characteristic 2. And not only that, the set of convex bodies have this compactness property with respect to like Hausdorff thing. So you see that not only this is not a volume polynomial of convex bodies, but there's a whole neighborhood which is not occupied by Minkowski's volume polynomials. So you know for sure that there are missing inequalities in Brun-Minkowski theory. You just don't know which one, how to write down one, but you know this vacant region that is not implied by this basic, like a Hodge index type or Alexander Fenchel type inequality. And then this is the attempt to precisely formulate this type of Brun-Minkowski question, like what do you mean by all the known inequalities and so on, was one other thing that led to the theory of Lorentzian polynomials.
Okay, good. Thank you very much. Good answer. Any other questions to June? Okay, if there are no more questions, let's thank June again. Thank you very much, June. It was a big pleasure to see you, and hopefully, I don't know, we see more your results on algebraic geometry, okay, in the future. Okay, thank you everyone for participating, and see you next week on Zach seminars. Bye.
Okay, bye. Take care, guys.
Bye. Bye.